What specific problem does your method aim to solve in the context of watermarking generative outputs from autoregressive image generation models?
Our method specifically aims to address the challenge of low reverse cycle consistency, RCC, in autoregressive image generation models, which can lead to significant discrepancies between generated tokens and those obtained after retokenization of the images. This lack of RCC can result in the loss of watermark information, especially when images undergo common transformations like JPEG compression or cropping. To mitigate this, we propose a fine-tuning procedure that optimizes the tokenizer and detokenizer for improved RCC, thereby enhancing the watermark's power and robustness against various transformations and attacks. Additionally, we introduce a post-hoc watermark synchronization layer to recover original tokens after geometric transformations, ensuring that the watermark remains detectable. Overall, our approach aims to create a strong, quality-preserving watermark that is resilient to both volumetric and geometric alterations in generated images.
Can you illustrate step-by-step how the proposed watermarking method works, including the roles of reverse cycle consistency, RCC, the fine-tuning procedure, and the watermark synchronization layer?
The proposed watermarking method for autoregressive image generation models involves several key steps. First, it addresses the challenge of reverse cycle consistency, RCC, which is crucial for ensuring that tokens generated by the model remain consistent when detokenized and retokenized. To improve RCC, a fine-tuning procedure is introduced that optimizes the detokenizer and tokenizer, allowing for better alignment between the original and retokenized outputs, thus enhancing watermark power and robustness against transformations like JPEG compression. Next, a watermark synchronization layer is implemented to handle geometric transformations, e.g., flips and rotations, that can disrupt token sequences. This layer embeds localized synchronization messages into the image, which helps detect and revert these transformations before applying the original watermark detector. The combination of these strategies results in a watermark that is not only strong and persistent, but also maintains the quality of the generated images, as demonstrated through thorough experimental evaluations.
Please provide a simple yet detailed example to demonstrate the inner workings of your watermarking algorithm, including the generation of tokens, the embedding of the watermark, and the detection process after transformations.
To illustrate the inner workings of our watermarking algorithm, consider the process of generating an image using an autoregressive model. First, the model generates a sequence of tokens representing the image through a tokenizer, which maps the image data to discrete tokens. For watermarking, we adapt the LLM watermarking method, KGW, by pseudorandomly partitioning the token vocabulary into green, watermarked, and red, non-watermarked tokens, embedding the watermark during the generation process by increasing the logits of the green tokens. After the image is generated, if it undergoes transformations, e.g., JPEG compression, we apply a detection process that first retokenizes the transformed image and computes a token match score. This score is then used to calculate a p-value. If the p-value is below a certain threshold, it indicates the presence of the watermark, confirming the image's origin despite the transformations.
What are the theoretical and practical benefits of your watermarking method compared to existing alternatives, particularly regarding the robustness and detection performance under various transformations?
Our watermarking method offers significant theoretical and practical advantages over existing alternatives, particularly in robustness and detection performance. Theoretically, our approach is grounded in the principles of LLM watermarking, providing provable guarantees on false positive rates and enabling the embedding of statistically detectable patterns directly during the generation process. Practically, our method demonstrates enhanced robustness against common transformations, such as JPEG compression and geometric alterations, through the implementation of a fine-tuning procedure that improves reverse cycle consistency, RCC, and a synchronization layer that detects and reverts geometric changes. Experimental results show that our watermark maintains high true positive rates, TPR, even under challenging conditions, outperforming post-hoc methods that are often fragile to such transformations. Overall, our watermarking technique is not only effective in preserving the quality of generated content, but also ensures persistent detection capabilities across a wide range of attacks and transformations.
How did you validate your watermarking method experimentally? And what datasets, benchmarks, and metrics did you use to test its effectiveness?
We validated our watermarking method experimentally by conducting thorough evaluations across 3 autoregressive image generation models: Taming, Chameleon, and RARXL. For each model, we generated samples using various configurations of our watermarking approach, including base, featuring, fine-tuned, and FT plus AUGs, fine-tuned with augmentations. We employed the ImageNet dataset for training and evaluation, generating 4 samples per model for 14 ImageNet classes and 4 COCO prompts for Chameleon. The effectiveness of our watermark was measured using metrics such as token match, TM, to assess reverse cycle consistency, RCC, true positive rate, TPR, at fixed false positive rates, FPR, and Frechet inception distance, FID, to evaluate generation quality. Our experiments demonstrated that fine-tuning improved RCC and watermark power while preserving generation quality, confirming the robustness of our watermark against various transformations and attacks.
What specific results did you achieve with your watermarking method? And how do these results compare to previously established benchmarks in watermarking for generative models?
Our watermarking method achieved significant improvements in robustness and power compared to previously established benchmarks. Specifically, we demonstrated that our fine-tuning procedure enhanced reverse cycle consistency, RCC, resulting in a true positive rate, TPR, of the watermark detector that was consistently higher across various false positive rates, FPR, compared to the base variant, which had a TPR of 10% at an FPR of 1%. Additionally, our watermark maintained quality preservation, with FID scores remaining below 150, indicating no degradation in generation quality. In terms of robustness, our method outperformed post-hoc watermarking techniques, which were either fully removed by geometric transformations or not robust to attacks like adversarial purification and neural compression. Overall, our approach not only provided a strong watermark, but also ensured persistence under a wide range of transformations, setting a new standard for watermarking in autoregressive image generation models.